Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, remove k digits. So basically we have a string number that represents just a positive number, and we have an integer k, and we want to return the smallest possible integer after we remove k digits from this string, and this string represents the number. So for example, for k equal to 3, it's better for us to remove 4, remove 3, and 2. So we'll end up with 1219. You may think at a first glance that it's better to remove the highest numbers, but that's actually not the right approach, like you see with this here. Because if you remove just the highest numbers, you remove this one, then you will end up with 1221, which is bigger than this one. Okay, so that's just something to think about. Now, in terms of the constraint, that it's really big, 10 to the power of 5, so that tells us we need to do something more efficient. And yeah, so that's pretty much the problem here. Now, how can we tackle it? Okay, so let's see how we can do this. Well, the first thing, as I said, you may think the first approach you may think about is, okay, let me just remove just the highest elements in the string first, right? So, but as we showed in this example, if you remove 9, 3, and 4, because those are the 3 highest, you will end up with this number, but this number is bigger than this, okay? So immediately that approach doesn't work. Now, another approach you may think about is, well, since I don't know, let me just try every possibility, right? Basically, you can do backtracking and just say keep position I, try keeping it, or try removing it. Okay, and then you do this only if you still have k, the remaining value of k is bigger than 0. You could try that, but then what's the possible states you can have? Well, up to I numbers at least, right? And that's, in each one of them you have 2 choices. So 2 to the power of I, and this is 10 to the power of 5, right? So that's immediately going to be too expensive. Okay, so that's not possible. What else can we do? Well, let's think about the numbers here. Why didn't it work, for example, for this one? Why didn't the 9 work here? Because of this 2 and 1. Between 2 and 1, if you look here, we want to remove 2 to get 1 in front, because with numbers, if you have like 9, 1, 1, 1, this is better than let's say have 1, 9, 9, 9, right? This is better. This is bigger, right? This is smaller. What I'm trying to get at is basically the most significant digits, right? It matters more that the most significant digit is the smallest. And so what we want to do with this problem to get the number to be as small as possible is to minimize the most significant digit. And by the most significant digit, I mean the ones in the front. Let's actually use the front numbers, the numbers in front, okay? So that's the important part. Now, how do we do that? Well, maybe we can just, as long as we have numbers to remove, if we find, let's say, 2 numbers as we are traversing the array, so let's say this is digit 1, digit 2, as we are traversing the string number, digit 4, anytime digit 1 is bigger than digit 2, just remove digit 1, right? Because if you have 4, 1, right, we should remove 4 and keep 1 regardless of what's in front, because as we said, the smallest number, the front number is what is the most important to minimize, right? So if you have something like this, regardless of what numbers are here, if it's 9999, let's actually, even if it's this one was like, let's say, the biggest number possible, let's say like this, it's always better for us to remove this 4 instead of removing anything else, because that will get the front number to be 1, right? And you can't beat that, right? So that's the first observation. The first observation is that if, let's actually call it observation 1, basically if, let's say, what is this? This was num I is bigger than num I plus 1, and we need to remove numbers, just remove the number at position I, okay? So that's the first observation. Now, if we extend this a little bit more, what if this was what if we had actually here 4, 5, 6 to 1, this number, for example. Now, what should we do? And let's say k equal to 3. Well, in this case, it's better to remove, let's say maybe this is 3 even, right? Well, and this is, just to make this super clear, let's say this is 9, 8, 7, right? Now, in this case, k equal to 3, well, it's better for us to remove this 3 in front number and get to 1987. Okay? Any other approach, let's say maybe we don't remove this 3, you will get 4, 5, and let's say we remove the 2, you get 4, 5, 1, 9, 8, 7. Sorry, we remove 4, we keep 3. We said we keep 3. So this number is bigger if we don't remove 3. And you can follow this idea basically all the way through, because if you keep these 3, then the number in front would be bigger, right? And so the overall number would be bigger, right? Because 4, no matter what's here, is bigger than 3, no matter what's afterwards. As long as what's afterwards is the same length, and that's the case because we have the same string, right? Now, with that, what I'm trying to get at is basically, let's say, looking at 2, we should remove all the elements to the left that are bigger than it, right? All the elements to the left that are bigger than it, as long as we still have numbers to remove. Now, how do you accomplish this? Now, with this observation, we could have just went through and did like for I in the range of the length of num, right? Okay, and just do this if check, right? But what I'm saying here is that we actually need to keep track of all the elements in the left so that we can know to keep removing, right? Actually, let's have this, because this 3, so 4 is smaller than 5, so this condition won't be valid, so we will keep 4. 5 is bigger than 3, so we'll remove 3. So we'll remove 5. But what if we had 6? Well, if we had 6, then 5 is still smaller than 6, so we don't remove it. But when we get to 2, we'll find, okay, 6 is bigger than 2, so we should remove 6. But we shouldn't stop there, right? And so this is not enough. So what we need is to actually say, what are all the elements to the left of 2 that are smaller than it, right? And so that's where you should think about a stack, because stack will allow you to keep track of the ones to the left and be able to remove them each time. So for example, here, let's say we'll put 4 because it's not qualified for removal. We'll put 4, we'll put 6. And then when we look at 2, we'll find 2 is smaller than, 6 is bigger than 2, so we remove 6. We'll check 5. 5 is bigger than 2, so we should remove it. 4 is bigger than 2, so we should remove it. And now we are left with this. And so a stack will allow us to accomplish this. And now in terms of what is this stack, this is just like a monotonic stack. This is just something to know, because it keeps the stack increasing. So if you saw earlier, we had 4, 5, 6. This is increasing. When we encounter 2, we are not going to put 2 on the top, because this violates the order of monotonically increasing stack, right? Because now it's decreasing. So what this means for a monotonic increasing stack is if we find any number that if we put will violate this increasing condition, we'll just remove all the elements that will, and then we'll add 2, okay? And so that's basically the concept of monotonic increasing stack. But, okay, so now what should we do? Well, we should just keep track of the stack to keep track of the previous numbers. But here, instead of doing if num I is smaller than num I plus 1, we can just check while. As long as what's at the top of the stack is bigger than the current element we are looking at, we should pop what's at the top of the stack. And of course, also as long as we need to still remove some numbers, right? And as long as we still have some elements in the stack. And that's pretty much the idea here of the logic. So let's just do that here. So we need a stack equal to like this. And let's go through just the digit in number, and this is just will be the digit. Now if the number on top is bigger than the digit, that means we need to remove it, because that means this digit is better to be at the front instead of this one. And then once we do that, if this is not bigger, we should add the element to the stack, right? So that's what we do here. And now once we are done, there may be some cases where, let's say for example, if we have 1, 1, 1, this element, and we need to remove 2, for example, out of it. Now in that case, this condition will never be true. But we still need to remove any 2 1, 1 values, right? And so that's why we need here, as if k is still bigger than 0, and we still have element in the stack, we should remove them. It doesn't matter, we can remove just from the top, right? Because this means there was no element that was bigger remaining, right? And so here we do k minus 1. Now once we are done, we can just join what's still left in the stack, like this, because we removed k element. And here we can actually do this. Let's try this. Now there is one case that we need to handle, which is, what if this stack is empty? Let's say we had this and k equal to 3. So we had to remove all 3. Now we have empty string, but that's not a valid number. We should return 0 for empty string. Like for example, if you look at this one, 0, k equal to 2. When we remove the 2 elements, empty instead of empty, we return 0 and nothing is left. So we should do that here. You could do something like if stack, if not stack. So if stack basically is empty, returns 0. But I prefer to do just or 0 like this, so that if this is empty, we'll just put 0. Okay. Now there is another problem, which is for this use case here. For this case here, what happens is, let's say we want to remove 1 element, and so according to our rule, we'll find that 1 is bigger than 0, so we remove 1. But now we have a leading 0 that we need to remove. And so that's simple to handle, because we can just use this string and remove the front 0 out of it, like this. And that should handle that case. So let's run this. Okay, looks like still there is this here. So let's actually just do it like, we can do something like this. Basically, let's just have s equal to this. Because if it's just 0, else strip will strip it, and we will have just empty string. And so what we should do here is just do like this. And if not s, so if s is empty, then let's just return 0, just to safeguard against our case here. Okay. Now if we run this, it should work. Submit. And it does get accepted. Now in terms of time complexity, this loop here is O(n). Now because the stack at most will contain the number of elements in the array. So overall, in aggregate, this will run only n times. And this is O(n) at most as well. And so overall, it's O(n) time. We are using this stack, so that's O(n) space as well. Yeah, so that's pretty much it for this problem. Thanks for watching, and see you on the next one. Bye.